Welcome to Crystal Clear Chemistry channel. In order to crack either JEE mains or NEET exam, it's very important to strengthen our basics of any subject like maths, physics or chemistry. Through this channel, let's strengthen our basics of chemistry, and in this video, we are going to focus more on the buffer solution and the solubility product concepts as part 5 of ionic equilibrium. For the remaining parts and all, you can go to the playlist, then definitely you will find the videos, and definitely these videos are helpful. If you really like the video, please like, share and subscribe to my channel. Without any delay, let's get into the buffer solution now. What are buffer solutions? Suppose if we consider a solution which is in a beaker, and if we add acid to it, if we add small amount of acid to it, we know that it produces H plus ion in the aqueous solution, and immediately the pH value decreases because the acidic nature inversely proportional to the pH. But there are some type of solutions, there are some mixture of solutions, though we add acid, small amount of acid to it, there is no change in the pH at all. What does it mean? Even after adding the small amount of acid, why H plus ions are not increasing in case of some special mixtures of solutions? Okay, let us suppose that there is no change in the pH. Then the type of solutions are called what? Then the type of solutions are called buffer solutions. Instead of acid, if we add base to it, definitely pH should increase. But after adding the small amount of base to the type of those type of solutions which are called buffer solutions, there is no change in the pH. Let us see why the H plus ions are not increasing even if we are adding the H plus to some of the solutions. Okay, through the example only we will able to understand why the solutions are resisting the change in their pH values. If we consider a mixture of CH3COONA and CH3COOH, which is a weak acid, and it is the salt of strong base, which is nothing but NaOH, which is nothing but NaOH. Now, if we take that weak electrolyte in the aqueous solution, it splits into CH3COO minus, CH3COO minus plus H plus, right? As it is a weak electrolyte, equilibrium will be established. And when we add CH3COO minus or CH3COONA, it is a strong electrolyte. No doubt it splits into CH3COO minus plus Na plus ion. Now the solution is of more number of acetate ions, right? Acetate ions. Now the mixture of these two can act as a buffer solution. That means when we add small amount of acid like HCl, the H plus ions from the HCl readily react with this acetate ion and readily forms undissociated acetic acid molecules. Undissociated acetic acid molecules. So that means whatever we are adding the H plus ions in the solution, those are converting into undissociated acetic acid molecules, which are weak electrolyte molecules. Hence there is no change in the H plus ion concentration. That means there is no change in the pH value. Understand or not? So There are some mixtures are acting as a buffer solutions, and they are resisting the change in their pH value. Now let us see what type of solutions or what type of mixtures are acting as buffer solutions. Let's take another example here. Suppose if we consider the NH4Cl plus NH4OH mixture, in which NH4OH is the weak base and NH4Cl is the salt of strong acid like HCl. And whenever these two are in the solution of the solvent water, NH4OH exists in equilibrium as it is a weak electrolyte, and NH4Cl completely dissociates as it is a strong electrolyte, NH4 plus Cl minus. Now the solution is of more number of NH4 plus ions, ammonium ions. Now for example, if we consider this particular solution and if we add a strong base like NaOH in a small amounts, if we add NaOH in a smaller amount, then it immediately produces OH minus ions. Whatever the OH minus ions are produced here, they readily react with ammonium ion and forms undissociated NH4OH molecules. This time also, after adding the base to the particular mixture, OH minus ion concentrations are not changing. No change in the OH minus ion concentrations, because OH minus ion concentration, because whatever the extra base we have added, the OH minus ions are immediately converting into the undissociated NH4OH. Okay, so that is the reason why there is no change in the OH minus ion concentration, and hence the mixture of these two can also act as a buffer, can also act as a buffer. In fact, it resists the change in the pH when we add base, hence it is called a basic buffer. Hence it is called a basic buffer. And whatever we have seen in the last case, that mixture is called a acidic buffer. That mixture is called acidic buffer, because after adding small amount of acid, there is no change in the pH value. And now let us see what type of mixtures can able to act as a acidic buffer and basic buffer. Okay, suppose if we consider the mixture of weak acid and salt of strong base, only this type of mixtures can act as acidic buffer. And the other examples for acidic buffer are nothing but, let's take a weak electrolyte. We can also predict, or we can also write the buffer mixtures here. Let's write acidic buffers here. Suppose if we consider a H3PO4, it is a weak acid. I'm going to take NaOH, which is a strong base. Salt of this weak acid is nothing but Na3PO4. So H3PO4 and Na3PO4 definitely can act as an acidic buffer. Definitely can act as an acidic buffer which resists the change in pH. Similarly, if we consider HCl, and if we consider other example like CSOH also basic buffer, CSOH is also a strong base, right? So it's a salt. If we consider CSCN, cesium cyanide, the mixture of these two can act as an acidic buffer. Like this, we can quote many examples. If you know the weak acid and weak base, strong acids and strong base examples, all those examples, some of the major examples I have given in the last video in the part 4. You can check in that video. Okay, anyhow, let's move to the next buffer, that is basic buffer. Let us see the examples of it. The one with the weak base and salt of strong acid mixtures can act as the basic buffers. Can act as basic buffers. The examples for basic buffer are, if we consider NH4OH, it is a weak base, and let's consider the salt of strong acid, I'm going to consider the strong acid as H2SO4. Then its salt means ammonium sulfate. So NH4 twice SO4. The mixture of these two can again act as the basic buffer. And not only this one, if we consider the organic compound like pyridine and pyridinium chloride can also act as a buffer solution. So we can give many examples if we know the basic principle here. We have to take the weak base and the salt of strong acid. Now listen carefully, very interesting point and important. That is, there is also the third type of buffer apart from acidic buffer and basic buffer, that is nothing but neutral buffer. What it is called? Neutral buffer. If we take weak acid plus strong of salt of strong base, acidic buffer, basic buffer, then what type of mixtures or what type of compound can act as a neutral buffer means it is a single compound solution. Neutral buffer solution is a single compound solution, and that single compound is a salt first of all, and that salt is obtained from weak acid and weak base. The salt is obtained from the weak acid plus weak base. Suppose if we consider weak acid CH3COOH and NH4OH weak base, the combination of these two readily produces a CH3COONH4, which is called ammonium acetate. Ammonium acetate, which is the salt of weak acid and weak base, and in the last video we already discussed that it can undergo either cationic hydrolysis or anionic hydrolysis. Due to that, it can act as it can resist the change in the pH after adding a small amount of acid or base to it. Okay, so one more example we can give for the neutral buffer. For example, H2CO3 is a weak acid, and let us see another weak base. For example, if we consider NH4OH instead of NH4OH, let's take another example. Uh, let's take MgOH twice. It is a weak base, and the combination of these two is nothing but MgCO3, right? MgCO3. So the solution of MgCO3 definitely can act as a neutral buffer. Okay, very important examples these two for the neutral buffer. Okay, we came to know why and how the buffer solutions are resisting their pH values when we add a small amount of acid or base or even the water also. Even on dilution also, the pH is not changing just because of the principle involved here, that is nothing but the common ion effect, right? Here common ion effect also involved, and not only that one, it is because of that weak electrolyte, right, which makes undissociated molecules. Then how to calculate pH of these buffer solution? Henderson gave expressions for calculating the pH and pOH of acidic and basic buffers. Let us see what are they. So mixed buffers and simple buffers, if we consider, the simple buffers are nothing but the neutral buffers here. We know already about the basic buffers, right? Simple buffers are nothing but neutral buffers. Ammonium acetate is the best example. So you can see here the acidic buffer and examples, and the basic buffer also, the weak base and salt of strong acid. These are the Henderson equation for which we can calculate the pH value. pH is equal to pKa plus log of salt by acid. This pKa is nothing but negative logarithm of Ka. Ka is nothing but dissociation constant, and log of salt by acid. pH is equal to pKa plus log of N1V1 by N2V2. Because after mixing both definitely there is a change in the concentration. That change we can predict, or the change ratio we can take as a N1V1 by N2V2. Similarly, for POH we can say pKb plus log of salt by base. Okay. Now let's move to the solubility product. What is solubility product? The product of molar concentrations of its ions in a saturated solution. Each concentration rises to the power equal to the number of ions produced on dissociation of one molecule of electrolyte. When we take one molecule of electrolyte, for example Ba plus 2 plus, suppose if we consider BaCl, BaCl, it is converting into Ba plus 2 and SO4 minus 2. Here the number of ions produced are 1 Ba plus 2 and 1 SO4 minus 2, and concentration of these Ba plus 2 and SO4 minus 2 rise to their coefficients like Ba plus 2 power 1 and SO4 minus 2 power 1. In a saturated solution, this word is very very important. In a saturated solution is nothing but the solubility product. Okay, now let us see what is saturated solution, what is unsaturated solution. Is there any solution called supersaturated solution or not? Okay, let us briefly know what they are actually. Okay, right. So solutions if we consider, they are of three types. They are of three types. They are nothing but unsaturated solutions, saturated solutions, and supersaturated solutions. By taking an example, we can easily remember what are they. In fact, let us suppose that in a glass of water, when we add 3 spoons of sugar, after mixing with the spoon it completely dissociates. 3 spoons of sugar, if we, after adding the 3 spoons of sugar completely dissociate in the water. After adding one more spoon, let us say it is also completely dissociated or dissolved in water. Okay, that means this glass has now the 4 spoons of sugar. Let us suppose that after adding one more spoon sugar to that particular solution, it does not dissolve and it simply settle down at the bottom. That means the maximum capacity of this glass of water is 4 spoons of sugar it can able to take, right? 4 spoons of sugar can be dissociated in that one glass of sugar. When we add a fifth one, it just settle down at the glass, settle down at the bottom of the glass, let us say. Then what we do generally to make a sugar solution or sugar syrup, we generally heat, right? So after heating this glass of water with the 5 spoons of sugar, let us say the no doubt the fifth spoon of sugar also dissociates into the water, and in that particular case the solution that is present in the glass is called a supersaturated solution. When once the solution in the glass is cooled, then whatever the excess salt is there, then definitely that excess 1 spoon of salt precipitates out, or it just settle down at the bottom of the glass if we cool the supersaturated solution. Okay, so supersaturated means more than the capacity. If we forcing the solute to dissolve, then we get a supersaturated solution. Obviously unsaturated means if less amount of sugar is added, let us say some 1 spoon of sugar is added in 1 glass of water, then as it is able to dissolve some more solute into it, it is called unsaturated solution. Now listen carefully. If we consider the saturated solution, there exists equilibrium between undissolved salt, undissolved sugar and dissolved sugar. Continuously there exists equilibrium between the ions and the associated sugar particles. So we can compare this saturated solution, or we can say that there is equilibrium phenomena is involved in the saturated solution of some particular salts which are not completely dissolved. Those salts are nothing but sparingly soluble salts. Sparingly soluble salts. Those salts which are sparingly soluble, or you can say the capacity to dissolve in the solvent is less, definitely there exists equilibrium between undissociated particles and dissociated particles in the saturated solution. When once the equilibrium is established, whatever the molar concentrations of the ions are there, those ions concentrations product is nothing but solubility products. That's what they are saying here. Okay, now at any instant, when it is in the unsaturated situation, whether when it is in the saturated situation, or when the solution is at a supersaturated solution, whatever the ions concentrations product is there, if we consider that ionic product, if we consider ions concentration product, if we consider at all instants or at all times, we can calculate the ionic product. Let us say here as 1 is the concentration of sugar here, and here 4, and here it is 5, right? Just like that of the reaction quotient of the equilibrium, in terms of concentration products, we have two terms specifically. One is a ionic product and the other one is a solubility product. Ionic product is represented by QSP and the solubility product is represented by the KSP. At equilibrium, the ions product is nothing but the solubility product. What does it mean? When the system is at equilibrium, then QSP becomes equal to KSP. Just compare in, let's compare with that of the reaction quotient here. You will able to understand here. Okay, so conclusion here is the solubility product is nothing but ionic product only when the system is at equilibrium, means it is nothing but the saturated solution. Suppose if we consider the ionic product, in one of the case, if the ionic product is greater than that of the solubility product which is constant for a particular sparingly soluble salt like AgCl, then if ionic product is exceeding the KSP, then automatically we can say that the solution becomes super saturated, and definitely we can expect the precipitate of that particular salt. So the precipitate is formed when the ionic product exceeds the solubility product, and if ionic product is less than solubility product, then we can say that it is an unsaturated solution, and we can predict more amount of salt we can dissolve until it gets that equilibrium, until the ionic products becomes equal to the solubility product. So in order to know how much salt we can add to a particular amount of solvent to prepare a particular concentration, we have to know what is the solubility product, and we have to know how to calculate it, and the importance of this ionic product and the supersaturated solution concept and all, right? Now let us see the relation between the solubility and the solubility product here. As we discussed already, suppose if we consider the BaSO4, BaSO4 readily converts into Ba plus 2 into SO4 minus 2. Let us suppose that S is the solubility of BaSO4, nothing but the molar concentration. Then the concentration of Ba plus 2 will be S. The concentration of SO4 minus 2 will be S. The product of these two, if we consider S into S nothing but S square, this is nothing but a solubility product KSP. So KSP you will get it as a S square for this type of salts, for AB type of salts. Then what about these expressions? What about these expressions? Let us consider one more thing here. Suppose if we consider A to B, let us suppose that it is dissociating into 2A minus 2A minus plus B minus 2A plus B minus 2. As it is an electrolyte, let us suppose that there are two A plus ions and one B minus 2 ion in the solution of that A to B, which is a sparingly soluble salt. Then for S moles of A to B, there will be 2S moles in the solution. And for the S moles of A to B, there is a S mole in the B minus 2. So these are the concentrations. But according to the definition of solubility product, after taking the concentration, here the concentration of A plus ion is 2S, we have to rise to the power 2 again according to the definition, and hence we are writing 2s whole square into s, that is nothing but 4s cube. So for A to B type electrolyte it is 4s cube. So similarly we can able to remember for the remaining electrolytic types, they are nothing but 27 s power 4, 108 s power 5 and 256 s power here it is not, yeah, for AB4 and A4B type it is 256 s power 5. Okay. Now in general if we consider AXBY type electrolyte, for this type of AXBY salt you can see clearly the KSP value expression here. Okay. Now applications of solubility product. Predicting the precipitation of a salt. As we discussed already, if the ionic product exceeds the solubility product, the salts gets precipitated out. Okay. And by passing, suppose if we consider the HCl gas through the saturated solution of NaCl, the solubility of NaCl decreases and pure NaCl crystals can be precipitated out. Effect of common ion on solubility. Definitely the solubility decreases due to the common ion effect as the dissociation suppresses. Examples AgCl. When we add KCl to it, as the Cl minus is the common ion, AgCl dissociation suppresses and hence the solubility decreases. You can see here clearly. Okay. So that is all about the solubility product. Thanks for watching the video. If you really like the video, please try to comment and subscribe and share to your friends. Thank you.